Hello, my name is Lucas Jeans, and I am a second year student in the Bachelor's for Software and Electrical Engineering with ATU. I have chosen this project because I am passionate about alternative energy production that doesn't rely on the burning of fossil fuels or environmentally destructive mining of the Earth's resources.
My project is a smart solar panel array that can accurately calculate the position of the sun throughout the day in any given location on the Earth using a GPS module. And it can orientate the solar panel towards the most optimal angle with servo motors to receive the most sunlight for the highest voltage output, which is read by the ambient light sensors on the device. It can then send this position data along with the voltage readings to a web server for remote viewing of the device at any given time. Some of the UN sustainability goals that I plan to incorporate into this project are poverty, education, clean energy, and infrastructure. Providing a clean, renewable source of energy like a portable solar array can help to combat the inequality and provide the basic electricity needs of people around the world who may not have access to a dedicated grid for power. Or, in terms of natural disasters, it can help to supplement a temporary power supply to reduce the reliance on fossil fuel generators. Here is the backbone of my project, the solar elevation calculator that determines the vertical angle position of the sun above the horizon on a given day during the year. It is calculated using the formula shown here. This formula takes a number of variables including the latitude coordinate of the device of the Earth, the hour of the day, and the solar declination angle, which corresponds to the seasonal change of the maximum height of the sun above the horizon, which is different during the summer and winter solstices as an example. This formula plots the sun's track across the sky using the solar elevation as the vertical coordinate and the hour angle as the horizontal. Okay, now that I have explained briefly how the formula works, let us test the calculations and see how accurate it is. So, I will input the northern hemisphere for Galway as our base example here. And Galway is at the 53 degrees latitude position. And using the current date of the 17th of December, we get all of these values here. Now, I can compare these values with the current day values that we have. So at 12 o'clock or noon, the current elevation angle is at 13.58 degrees. And at 4 o'clock, which is around sunset, I get a value of -2. Now, there is a slight discrepancy of the values that I'm getting with my calculator and the true values for today, as there is a slight variation between the days that my formula doesn't account for. It is largely accurate with a range of between half a degree and 2 degrees, which is perfectly acceptable tolerance for my project, as my ambient light sensors have a range of up to 8 degrees before it starts to drop off in its max voltage. As my code is too mathematically complex to explain for the purposes of time constraints with the video demonstration, I will omit that for now. I do, however, have a light-dependent resistor set up as a practical example of how the ambient light sensor or solar panel will function in the final project. As I wave the light over the LDR, it outputs varying values corresponding to the voltage output I will be reading from the sensor that it will pick up from the sunlight that it tracks. I will be submitting these values along with the position data of the sun to the web server to give the relevant statistics of how the solar array will function over the course of the day. In conclusion, I will be building a smart solar array that calculates the path of the sun throughout the day anywhere on Earth using location and time data received from a GPS module. It will have ambient light sensors to read the voltage output from the light of the sun in lieu of photovoltaic cells of a solar panel, and using the same calculations from the formula, I can rotate the sensors using servo motors to follow the sun as it tracks across the sky. Theoretically, this solar array can automatically configure itself to accurately track the sun anywhere on Earth at any time. Once it turns on, it will do all the work for you, allowing ease of use for a rapidly deployable emergency solar power system that requires little to no user experience of the system. It can also be easily set up with one or multiple panels all managed by the same software. This has been my Smart Solar Array project. I am Lucas Jeans, a second-year student of Software and Electrical Engineering at ATU. Thank you for watching.